to do anything because the gradients actually really helped with the color balancing to begin with, but that's just kind of that. And then we have this contrast adjustments that we're applying once we have the gradients corrected, and then I do apply a banding correction that again might be really hard to see. But you can kind of see it. It's more of a vertical one than a horizontal one, but it does exist. And then the final tweaks is the ones that include sort of that last bit of noise suppression here. Oh, but this is the wrong one. But it's great that we looked at that one. We want this one, and so this is the beautiful near cam image that Joe did. And then so the main thing with this one is that, first of course, we want to prescribe this hue saturation, which we've done. Okay, can't move it. There we go. And then we, of course, want to screen this over actively. So it's this one's quite an easier one. Generally, there can be more color confusion, but these separate very nicely. But the real thing we want to do again is make these adjustments so that you are preserving the white balance, or sorry, the color balance. So you don't want to see like the outline of red. You want to make sure that you pulled it down enough so it all blends together. Now, in this case of this combination, sometimes you have to crop the image to accommodate the new mirroring data, because they don't usually, align exactly. Their fields of view can be quite different, but this one is nice that it like really just blends very nicely with the mirror image. So we didn't have to do any changes to the original orientation and crop. All right, I'm gonna move it on to Joe.
Okay. All right, we're getting into the home stretch now. Really appreciate everyone who's stayed this long.
It's long.
Yeah, it's kind of dry. Hope you like it. We're going to go back to our old friend, the Pillars of Creation, and I'm going to show you how the mirrored image of the pillars was put together. It's a very different looking view than what we saw with NearCam. I'm not going to go to the archive, but of course the data are in the archive. Here is the masked webpage with a filtered search that gets you just to the data we're looking at, the mirrored observations of the pillars. And then the first look in fixed insight of the data. And for this one, I actually wanted to show you really quickly. I'm going to pop out here. These little extra bits, we call these the mirrored snacks. That's because of the way the detector is actually built. So this whole image here is the whole focal plane of web and focusing in on the mirror instrument. So when we get imaging data from MIRI, we see this is the main area where images are taken, but then there's this extra little bit here, which is usually used for coronography, but also for any imaging data that always comes in as sort of like bonus data. So that's where these like sort of extra little bits of data that hang off the sides come from. This is a mosaic of clearly at least 1, 2, 3 by 2. So I think it's a 3 by 2 mosaic of MIRI, and then of course on one end you're getting the little extra bits there, which unfortunately you have to get cropped off. I can't leave those there. For this one, I'm actually going to try jumping into fixing source image here for linear fit, and then I'm going to apply linear fit to the other two images. So you can see the pixel values change slightly. And then I will use a tool called channel combination to create the color image. Okay? So for this one, I've already loaded it up, and I'll just hit the circle button to apply global. And we already see we have a color image here. I'm going to apply my stretch. I'm going to try doing a linked stretch. That's not ideal. Even with the linear fit, I'm still seeing like a strong color cast in this image, so I'm going to unlink the channels, and we'll use this as the initial color composite. And of course, I'm going to rotate it because this looks really strange. Okay, so that would be where I would now take this from Fixed Insight, save it out as a TIFF file, and work in Photoshop. This image, the colors came together pretty nicely, sort of like immediately, but it does have a lot of artifacts in it. You can see, there's these like different regions where colors aren't mixing well together. These are like edges of the detector that became mixed in with the mosaic, and it makes it more difficult, of course, to process the image, but this is like a region of the detector that is less sensitive than everywhere else that made it through into the mosaic and then became part of this color image. So that's an artifact that I'll have to deal with later. Okay, yeah. I'm going to jump over to Photoshop now. So here is that initial color composite. I brought it into Photoshop, and I'm going to first apply a curves adjustment. I think for this one I was using a neutral gray. You know, I'm kind of going back against what I said earlier, but I'm like just trying to play around, move around the image, find something that looks reasonable. I think I ultimately decided to use this region right here and define that as neutral gray. As you can see, there's a lot of subjectivity when it comes to images sometimes. I really prefer like the deep field images where we have like a very methodical way of color balancing the image. An image like this is a little more subjective, and it's a little more up to the individual image processor to get something that looks good out of it. But that's how we get to the color curve step. Here I'm just using a masked color curve to deal with this excess background region, trying to balance this against the rest of the image. And then this, I believe, I was just applying, yeah, okay, so this is, I think what I did here, I probably rasterized the image, but it was probably my first attempt at fine-tuning the color adjustments with camera raw. And then I worked on the clean. It's just one image, so I can't really go through the steps involved. But basically, it was just very, very carefully going through with clone stamp and just cleaning this up as best as possible. With, you know, unfortunately, I am introducing information here that's not there.
Isn't that photoshopping, cloning, clone stamp?
Yes, that is Photoshop. Right.
But these images are used for public relations, not used for science, right?
That's right. Yeah, we always tell the scientists you would never do any kind of scientific analysis with the images that we produce. It's a useful sort of insight into what's there, because we can produce an image that shows really interesting color variations in a way that scientists usually don't have access to. But in terms of doing like flux analysis or real scientific analysis of the image, you would never use something like this to do that.
PixInsight, it came from amateurs, so then I was curious, how did you come across PixInsight? By reading the amateur astrophotography forums?
Yeah, and I've done some amateur astrophotography myself, which is how I first learned about it. Further cleanup of the image here, again dealing with the excess background region with a curves layer, another color curves adjustment plus camera raw, and then final color adjustment, final image. Okay, yeah, those last few steps do make a difference. But what I really wanted to get to was to talk about the combination of the MIRI data with the NearCam image. So we'll jump back into the presentation for that. This actually brings up an interesting story of the origins of what we refer to as near MIRI-cam, which came about during the web's first images. And where that came from was that when we took the image of the Carina Nebula, the cosmic lucid Carina, we actually did, we took a MIRI image of this region as well. It's a smaller area, but this was the MIRI image. And this is the combination of MIRI and NearCam here that we're seeing. So we'll zoom in on that. Okay, so when the data first came down, the Carina Nebula, NearCam plus MIRI, this was the selection of filters that I had to work with. And following our logical chromatic ordering of color, I initially started with assigning colors in this fashion, where most of the NearCam data were in the blue and the green, and then MIRI, because it's the longer wavelengths, then moves into the yellows, oranges, and reds. However, the color image that comes out of that looks like this. This suffers from several issues, color being one of them. And one of the main reasons is because, as you know, the NearCam image has a ton of stars in the background, that when you get into mid-infrared wavelengths, those stars go away because now we're seeing the gas in front of them that's glowing. So when you do a combination of NearCam and MIRI in this fashion, where you've assigned the bluer colors to NearCam and the orange and red to MIRI, what you end up seeing is pure blue stars, which just does not look natural. It creates a very difficult to interpret image. We're not used to seeing pure blue stars. So I decided to take the next step and see, well, what does the MIRI image look like on its own? What if we just apply the same chromatic ordering of color to just the MIRI data? So now I'm taking, kind of the approach that I just took with the pillars image earlier. I'm using the available data that I have from MIRI, which is 4 filters, using chromatic ordering of color, and this was the image that came out of that. So when I saw this, I thought, okay, this looks really nice. This is a really beautiful color image. And it's also very, very different from what we saw from the near-cam data. And it actually caused me to think of Monet's paintings of the Rouen Cathedral in France, and how, he spent many, many hours painting the same scene over and over and over again in different conditions, in different atmospheric conditions, trying to capture the essence of the lighting and the shadows and the atmosphere around that scene at different times of day, right? So if it was in the morning, it had a certain look. In the afternoon, a very different look. In the evening, with sort of the golden hour of light coming from the sun, another totally different look. So I thought, what if we could take what we got from the Miri image here and sort of take the best of Miri, combine it with the best of near-cam? How can we do that? So that was when it occurred to me to try and interleave the data together instead of going purely chromatic from shortest wavelengths to longest wavelengths. What if we took the near-cam data and mixed it in with the Miri data so that the shortest wavelengths of near-cam and Miri are blue, and so on and so forth as we go into the longer wavelengths. And that was how this image came about. Now, you may say that we're breaking the rules here because we've sort of broken the chromatic ordering, but there is still astrophysical meaning to the way the colors are assigned. This region of Carina has embedded stars that are deeply embedded in gas and dust that are in the process of forming. Those stars, some of them have jets shooting out of them. They should be very red and dusty, and because of the way we've preserved the color ordering in both near-cam and Miri, they actually do preserve that information. So like this region right here, there's a star that's deeply embedded in this cloud. It shines very brightly in the Miri wavelength, so it shows up here as a very bright white source. But it also has a lot of red around it, indicating that it's a very dusty source embedded in a cloud. In addition, it has these jets shooting out of it that you can kind of see the bow shocks down here and here. All of that is possible because of the ordering of color here. Additionally, the stars have a much more natural color to them. We've been able to preserve the color information from the near-cam data, so the bluer stars are actually bluer and the redder stars are redder. And then, of course, the Miri data is showing up as well. Where those stars are the brightest, those are the ones that are really deeply embedded in clouds of gas and dust, and they're showing up redder here. So I took this philosophy approach to the Pillars of Creation image when we combined the Miri and near-cam data. Now, essentially, what we end up with here is you take the color image from Miri, and you take the color image from near-cam, and you literally just put them together and blend them. So first you have to align them, of course, and that can be done sort of like what Alyssa was showing with Cartwheel. I wouldn't say it's easy, but you can go in, especially if you have a lot of point sources like stars, and take one layer, make it the subtractive of the layer below it. So in this case, I took the Miri image, I believe, and made that blending mode subtraction over the near-cam image. So of course it doesn't look very nice, but it makes it much easier to find stars that you can use as a sort of pinpoint reference to do a transformation to the Miri image to then line it up to the near-cam image. It might be better if I just showed you, but if that question comes up, I will. And then this was the resulting image, which again is still astrophysically relevant. We have, deeply embedded star right here that is deep in this cloud. That's why this cloud shows up so dark, right? It's very, very dense. So even at the longest wavelengths of Miri, it's still very dark. And there is a star in there in the process of forming with jets shooting out of it, and it's very deeply embedded, it's very dusty and red, and it is showing up very dusty and red here as well. The outgassing, the sort of photoevaporation that's happening on the clouds from the nearby hot stars is showing up apparently here, or very apparent, as purple hues that's sort of separated from the overall nebulosity that we're getting from the Miri image that shows up as oranges and reds in the background. And then down at the bottom here, this is a region where there's a sort of a shock front from another jet that's off the screen because it wasn't captured in the Miri data. But that is showing up more blue here because it shows up very strongly in the shorter wavelength ranges of near-cam. And so overall, we've been able to preserve all of this astrophysical information, but also produce a really aesthetically beautiful image that really captured people's attention. It's one of my favorites, actually. And that is the end. So if there are questions, we'd be happy to answer. Thank you. Is that a microphone?
Oh, yeah.
Can I get your name?
Joe Depasquale.
So do you do your astrophotography from the East Coast?
When I can.
Yeah, I'm just wondering how the heck do people in the Midwest need to deal with the cloud? I'm from the West Coast. It's usually clear.
Yeah.
Hi, I have in terms of like ordering the well, have you thought about doing the reverse color order, I guess?
So reverse color order, you mean like the shortest wavelengths with the red?
Yeah.
Yeah. We've tried that before. It actually looks very strange. And it breaks away from the physics of why we do this, right? It goes back to the eyeball and how we perceive light and how shorter wavelengths of light are bluer, longer wavelengths of light are redder. That holds in the visible wavelength range, and it actually really works well sort of across the entire electromagnetic spectrum whenever you're combining data from multiple wavelengths.
Hello. So earlier you mentioned that you might work with scientists to highlight certain data within these visualizations, and you might take a wavelength and assign it a color that doesn't make sense in the color mapping that you're using. Can you give a practical example of what kind of data you might assign a specific color just to highlight in an image like this?
Yes, well, I'll say in general, yes, we do like to stick to chromatic order when we can, just because, again, because of the physical meaning and how it relates to, higher energy, bluer, longer wavelengths, lower energy, etc. But again, yeah, in order to showcase certain features, especially narrowband data, this is really where narrowband data comes to play, because narrowband data is capturing like hydrogen emission, ionized gas. So it's like a very specific chemical composition that we're very interested in. So this might be iron that the PI is interested in. So one of these examples is actually the Carina Nebula, where, it's not a true reach of chromatic order, just because it's hydrogen emission that would have been captured in the wavelength of 2.2 microns. So it's kind of hard to showcase without like the numbers, sorry. But basically, this was the 4.7 micron filter that you see in yellow. So this jet is the hydrogen emission. That's very important because if we just added red to a 4.4 microns, which was red, or in sort of the higher regions, then you can't differentiate the different colors. And so we need to move it in a place that is both aesthetically and it's compatible with the rest of the data, but like stands out. Now, again, this wasn't a true reach because what you see in 4.7 is actually very similar to what you see in 2.12. So there's different sort of spikes in emission for different sort of elements and atomic transitions, and this will be captured by both of them. So it's like, it was okay, and like the PI was like, it's okay to do this. So like, we got the okay from the scientists, so it's all good. Actually, I think it's interesting is that I feel like the scientists tend to want to break chromatic ordering more than we do.
That's very true.
Yes, because they're just like, we want that to degree. Because they're thinking of representational, like, they're thinking of their scale bars, their color maps that are, various colors, just red, greens. And to us, we're like, well, that's visually terrible. It's a balance, of course. I'm trying to think of other examples. There's not a ton. I think Crab Nebula is one of them too. It's generally something only we do for narrowband data, because narrowband data is different in that, again, it's just a very specific structure. And so broadband data, it can overlap, and so those colors help to get that full color space, that full color gamut coverage. But when it comes to narrowband data, it's something that you can just overlay on top that doesn't affect anything else. So if that just one little narrowband thing that doesn't affect anything else, and you can just overlay that on top, then that's something that will reach.
Hi, I am not here at SIGGRAPH because I am an astrophotographer, but I am an astrophotographer also. And I am French, and in France, we use a lot of STSci, which is a European software from Spain. And I'm very happy that here in the United States you use also this marvelous software. But my question is that in Europe we don't use the same color palette. Usually, and I have noticed that your image are with a very high contrast, with very clear colors. In Europe, we are used to use a lighter palette and soft colors. And I want to ask you if you know these differences and why here in the United States there is always very contrasted pictures, and in Europe, in fact, when we see such image, we call them American style pictures.
I love that. Well, I think I have to argue with you on that because the Euclid data I've been seeing that has come down recently this year, I would argue Euclid observations have been processed in a way that is similar to what we've done with Webb. They are high contrast, and the whole point of Euclid is that it's looking at a really, really large region of the sky. But it also has to be like an aesthetically pleasing image, right? That's the whole driving force behind getting these images out there for the public to see, to take them in. They need to be dynamic. We're not trying to like overdo it, oversaturate things, but we want to make an image that really captures your attention. I don't know if you have anything.
Oh, I just wanted to add that gamma is a little different than our screens, if that makes any difference. So I agree. I think it's difficult to know when to stop, but yeah, like that looks a lot more saturated to me than the screen does. So I think this plays a little bit of a role, but in general, I think it's just like an aesthetic that was probably formed before us, and something that we're just trying to like stay, consistent with for clarity reasons. And again, like Joe's saying, like a lot of this is like for the public. So this is not for, like, even though the scientists benefit from this too, because not only does their science go out there, but then they can look at an image and actually decide from the image, like, oh, I want to investigate further on this, particular star or object. So, but it's designed for the public for information purposes and to be engaging and dynamic. And so, again, like, it is a balance, and we definitely don't want to overdo it. That's generally not something we try to do. We try to let the data kind of speak for itself, but we do enhance it, and a lot of it. A lot of the scientists are very interested in really seeing the differences in those filters. So they want to be like, that's the ionized hydrogen, and they're like, make it brighter.
Yeah, oftentimes we have to like push back a little bit and say we don't want to take it that far, right? Like, a nicely color balanced image will speak for itself. It doesn't have to be pushed so far.
Hi, hello. So I joined the bit late, so apologies if you already covered this. And my question has nothing to do with colorization or wavelengths or anything like that. So these 6 lines that we see in every star, I understand those are some sort of diffraction artifacts produced by the equipment, not there, of course. But they make the picture very pretty. So do you ever do any effort to remove all these diffraction artifacts, or they are too difficult to remove? And also because the image is great and very Christmas and leave them alone? Yeah.
Yeah, that's a great question. I've actually had people accuse me of adding them in there after the fact, like as a post-processing step, right? To add in the sparkle. But no, as you said, it's an artifact of the optical system of the telescope. And there are cases, I think Alyssa answered a question similar earlier, where we do attempt to remove them if they are interfering with the main part of the image, like the science point of the image. We have taken them out for that. There are cases where there's a bright star off of the field of view of the image that has lent in like a giant stripe across the image. We will remove those as well. In this case, actually, there is a star just off the field of view here, and it's contributing these lines that we're seeing. But we decided to leave those in because it's actually signifying that there's a very bright source just above the field of view here that is causing all of this glow that we see just above the clouds. And so that was an aesthetic choice to leave those lines in there. Yep.
So I kind of want to build off this gentleman's question or continue on that. So you mentioned that this was an aesthetic that was kind of established before your time. So I guess my question is, who approves the image? Who has final approval? So you mentioned that the scientists will ask for certain things, he'll push back. When you were talking about combining the NIRCam and MIRI data and we were experimenting with the chromatic order, and you were making the decision as this is what I think looks best. So, as the artist, you obviously have a certain amount of say, the scientists do. Is there a person who's like, yes, this is approved? Do you ever have to justify why you made the decisions you made? That's it.
Yeah, no, I definitely think it's like a balance between like the different expertise. So like there's the scientists, we're part of like a larger news team so we've been mainly discussing outreach images, actually, even though a lot of the work that we do is with science data, which is actually a little bit of a different process. But generally we have a news chief and we set up a meeting with these scientists beforehand, usually, to just get an understanding of the physics and any information we can. So we just kind of get a vision of what they're looking for to begin with. And then, so that will give us some insight, and then we'll go, make something, and then we'll share it. And so that will be our first iteration. I will say generally, it's a pretty smooth process, and usually we're pretty much on the same wavelength. So that generally works, but it is like we do share with the whole group, so it's not just the scientists, it's also like science educators, people that are like looking at this image and being like, this doesn't make sense to the general public. So there's a lot of different eyes that are looking at this from different perspectives, and we need to satisfy all of them. I think obviously our artistic expertise definitely plays a role, and if we tell them the limitations of the data or why we did this and that, like they will definitely be like, okay, that makes sense. I think it's probably like if the PI or the scientist is like, this is not right, like we definitely want to make sure that we fix that. So we'll never like put out a press release that hasn't been, scrutinized by the scientists. So I would say they get like the official final say and if we can put it out, but it's definitely like a combination of all of those.
Yeah, there's also a final higher level review at NASA headquarters of everything we put out as well.
So if it seems that the stretching is pretty early on in the process. If you don't like how the contrast is going, do you have to go all the way back to that stage, or are you going to do that on individual channels, or do you mess with normalization, or what do you do in those cases?
Yeah, I'll start and say that there have definitely been times where I've gotten pretty far through the process and I've realized that I really don't like what I'm doing, and I'll go back to the beginning. I don't like to start in the middle. Like if I don't like the stretch or the contrast of something, I'm going to go back to square one and start over. Because the process just evolves from there, and it's so important to get that stretch right in the beginning.
Yeah, no, I agree. That's usually why I try to keep my stretch, it won't be the best stretch, but it'll get me close, close enough that I can make those adjustments later on. But even then, sometimes you do have to revisit the image, and it seems strange that reprocessing the whole image would get you a better result, but sometimes it really does. And because you're stretching these things, the stretch actually makes color balance very sensitive. So even a slight difference in the stretch will give you a very different color balance. So yeah, you kind of have to be careful with that. And I think the most important thing is that if you ever accidentally sort of saturate something that shouldn't be saturated, you definitely have to go back. There are some times where you kind of don't realize that your not necessarily your star cores will be saturated, but if your galaxy cores in a deep field are saturated because you're trying to bring out that faint noise or the faintest galaxies, then you have to revisit because you don't. It's always a balance between, preserving the black and the white points.
I think we have time for one more question if there's any more.
Do you work with any amateur astrophotographers like Rob Gendler?
We have worked with Rob, yeah.
Who else?
Oof. Okay, let's go with Stefan Gizzard.
Yeah.
Wonderful. Gosh, there's so many. We've worked with many, mainly for like context imagery, because we are so limited by our fields of view by these telescopes. Very high resolution, but very narrow fields of view. So we rely on their ground-based observations to provide like context to a lot of our imagery. Or sometimes we'll use it as sort of color information, and then we use the high resolution of one filter from our space telescopes. The names are fading, but we do work with them. We're very grateful to all of them. Really awesome work out there. Oh, of course, Takes Insight tutorials. Adam Locke.
Yes.
But there's so many.
All right. Thank you everyone for sticking around.